In this video, I'm going to give you a recap of the continuous time closed loop control system. So this is the starting point to designing a sampled data control system where we're going to use discrete time control theory. So if you recall from your previous studies what an open loop system is. So here we're looking at an open loop system initially. System, the normal notation we use is G of S when we're in continuous time. So we've undertaken the Laplace transformation. You can see here the system contains an actuator. The actuator, I'm going to say, enables us to do so. It enables us to make change to the process. So what does it look like? So it looks like this. So if you recall, these lines with, in this case, we've got direction with the arrows on. These indicate a signal. These are used to represent a signal. Boxes or rectangles, squares, whatever, are used to represent some form of like dynamics going on within there. So in the case of an actuator, we could have a mathematical model that represents an actuator. So in this case, we're looking at the domestic heating system. It could be a heating element. It could be the actuator, it could be a DC motor. And then we have the process. So the actuator is going to do something, it's going to make change to the process. System input, U of S, system output, Y of S. So these are independent. So the input, in practice, it could be some form of voltage. So effectively, you're going to supply a voltage to an actuator. In the case of the domestic heating system, it's then going to create some change at the process. If you apply if you apply a voltage to a heating element, it's going to produce heat, and then it's going to result perhaps in the room heating up. And then that being the system output, so it would be the room heating up. If you remember previously, we can mathematically model the actuator and process using a transfer function. So whether it's first order transfer function looks like that, or a second order transfer function that looks something like that. Okay, so these could be used to model that. And the reason why we use transfer functions is because we're interested in control in representing systems in a relationship between the output and the input, and that's the transfer function form. So we normally start off with an ordinary differential equation. We then undertake the Laplace transformation. If you remember this Laplace symbol, we normally undertake the Laplace transformation on the f of t, whatever the function is it's looking at. It could be the ordinary differential equation, and then we result in in the case of these ordinary differential equations. And like I say, we move to the Laplace because it has benefits that we can put into the transfer function. Because once we move to the Laplace domain, so in ODEs we're working in time domain, in the Laplace domain we're working in the complex frequency domain. And what we can do is we can algebraically manipulate the ODE when it's converted into Laplace into a transfer function. That's the main benefits of why we undertake that process. So then in terms of when we're moving on to control, so what are we trying to do in control? We're trying to effectively manipulate, you could use the word control, manipulate the behaviour of a given system. So if we were looking at the heating system, obviously providing a voltage input to the actuator, and then that then would result in some form of dynamics at the process. It'd be heating or cooling of the room. But in control, what we want to actually do is we want to regulate the temperature. We want to control the temperature to kind of some form of desired value in this particular application. So what we introduce is the idea of feedback. Okay, so feedback is very important. And what we put in the feedback is a sensor that enables us to measure the physical phenomenon dependent on the application that we're looking at. So in this case, you think in terms of the heating of a room, heat, okay, it's obvious, temperature, so we need some form of temperature sensor. So you can see system output Y of S and then Y of S here. Y of S, these are equal because what we normally assume in control is an ideal. We normally assume an ideal sensor. So we normally assume that this has a value of 1 in here. Okay, so it doesn't have any kind of like amplitude drop. There's no noise that you might expect on an actual physical sensor. You would get noise on the sensor, but we're not assuming that's there. And then we introduce things such as filtering the signal. You'll see on when you get onto the embedded control. So then we measure the temperature, and what sensor you use very much depends on the system that you're looking at. So, for example, if I had a robotic arm and I was interested in, applying, I had some form of gripper, robotic gripper, and I wanted to apply a given force to an object that I was picking up. I'd probably use some form of force sensor. So it might be a strain gauge. If I'm interested in, I don't know, some form of longitudinal displacement system, I might have some form of sensor that's going to measure, some sort of sensor that's going to measure displacement. Or if I'm interested in angle, I might use a potentiometer. I don't know. It very much depends on the system. The physical phenomenon that's going on in here, in the process, in terms of the dynamics, will very much depend on what sensor you select. Right, so that's it. The sensors enabling me to see what's going on in terms of the state of the system. So I've got do, see. I then feed it then back into into this summing junction, the reference. So again, these lines here, the arrows, they're representing signals. Here I've got a reference, and here I define what my reference is. So in this case, I've said desired temperature 17 degrees Celsius. We then form an error. The error signal, keep it in the class, is effectively the reference take away the measured value. That's what we form in terms of the error signal. So here you can see we've got a difference in this particular case of 2, so our error would be 2. And here you can see the signals. So this is our measured signal, this is our reference, this is our error. What we notice, all the signals are continuous because we're working in continuous time at the moment. Then this error term would then multiply by this Kp, K over S, and Kd multiplied by S. And this is known as our free term PID controller. So free term PID controller. So proportional, integral, and derivative. Proportional is effectively just multiplying the error. The integral is looking at the area of the error, and the derivative is looking at the rate of change in the error. And if you also recall when we looked at tuning methods, all you're doing in the tuning methods is you're effectively changing these values of Kp, Ki, and Kd, and that's going to then change the system, the performance of your control system. And if you remember as well what these three terms are going to do, so proportional control, generally if you just have a proportional control on its own, you increase it, it's going to basically put more power into your system. It's probably going to result in more oscillations on the system response. The integral is going to eliminate any steady state error. So at the moment, if you think about that, our reference is 17 degrees. At the moment, we're getting kind of 15. Here, when there's a difference, that's known as a steady state error. The integral will eliminate any steady state error. The derivative, what that's very useful for is if you have a system and it's got kind of quite a lot of oscillation on the response, it will help reduce that. So these three terms combined are very, very powerful in terms of getting your control system to effectively do what you want it to do. So I'm going to put here think, but don't get confused thinking that the control system has the ability to think like the human brain. It's very much determined based on what these Ki, Kp, Ki, and Kd values are. So in terms of a continuous time closed loop system, this controller here would be implemented, it'd be hardwired, it'd be hardwired, it'd be an electronic circuit, and it'd be using an amplifier for the proportional, an amplifier for the integral, and an amplifier for the derivative in terms of actual practice. But obviously this is the theory we're looking at here. So that really is the fundamentals. So the sense enables you to see what the current state of the system is. The control then enables you to think, and the reference here, we're pretty much saying, well, this is how we want the system to behave. We want the system to be 17 degrees Celsius. We then would configure the control system, so you tune your control system such that it's going to work well for you. It's going to basically manipulate, control the system to give you this desired system performance. So a well-tuned controller in this case, you'd end up with, obviously if you're looking back at this graph, you would end up with something that would hover around, if we were saying that's 17 degrees Celsius, you'd hover around this here. Poorly tuned control, not very well tuned control, obviously you might get some steady state error, and you might get something that oscillates quite a lot around, and that's not going to be very efficient in terms of energy. So that really is the closed loop control system. So it works in a cycle continuously, and the whole idea is to try and achieve this reference by measuring and configuring your controller such that it can compensate for there being an error, and then your actuator enabling you to actually make that change based on the error. So the change that the actuator makes here is a function of this error. So if we have a big error, it's probably going to be, well, it could be a positive or negative error, I guess, depending on whether we're above or below this temperature. But it's going to result in the actuator maybe completely turning off, or it depends on the amount of power that's going to be provided to the actuator, and that's dependent on how you configure your control. This we are going to cover in the weeks that follow. As this is kind of a starting point. When we move on to sample data control system, you'll see this similar form, but with a few extra components. Just be aware that the basic function and how this works doesn't change for a sample data control system. A control system that works on your human body, a mechanical control system, an electronic control system, they all work in the same basic principles that look very much like this diagram, where you have the ability to measure what's going on in terms of your system, to compare what's going on in your system to a reference, and then to have your controller configured that it effectively can compensate for the error, and then the control output to be fed to the actuator, and then once it's configured well, to get good control performance. So hopefully this has helped you kind of get your head around the closed loop control system. This is fundamental for the following short lecture videos the short lecture videos that follow this. So if you've got any questions, please contact me. I hope that's been useful. Thank you.